Hey there, classes. Welcome back. Trying to bring together a lot of the things that we've done lately into today's and tomorrow's lectures and lessons. And we started with a little walk outside. We went outside. It was a beautiful, gorgeous sunny morning here in Pacifica today. And I wanted the students, one, to check out the shadows of the basketball court. The shadows are getting longer. Of course, we are in autumn now. And as we head towards the winter solstice, December 22nd this year, I believe, you've got the shadows getting longer and longer each day. That had to do with our tilt of our Earth's axis, of course, and so that was a nice little tie in there. And also feeling the sunshine out there. One of the things that I think is difficult when students are being introduced to chemistry is when you get into conservation laws. At first, it seems very straightforward. Whatever you start a chemical reaction with, you end up with the same number and type of atoms on each side of the chemical reaction. But then we also, in 7th grade and 8th grade, talk about nuclear reactions. We talk about radioactive decay. And I've been spending a little bit of extra time on ratios, proportions, because all of that feeds in to really understanding what's going on in a chemical versus a nuclear reaction. We see ratios in terms of when we do radioactive decay, it makes a curve instead of a straight line graph. So I was trying to introduce that and trying to get the ideas across in a couple of different ways. One goofy way yesterday was using my daughter's American Girl doll. Yeah, we have a couple of things around the room. I had a building over here, a little model building. It had the Millennium Falcon over there. We used an American Girl doll because we measured her height. Now, you can tell she's an American Girl doll because we used, if you check out in the box, it says they all come in a standard 18 inches in height. If she was a European kid doll, they would be measuring in centimeters. But we took advantage of that. We said, okay, how do you use a conversion factor properly to convert her height from inches to centimeters? And of course, we use centimeters in this class. And that gave us a good review yesterday, hopefully, on how we use conversion factors properly when we're laying out something so that we can cross-cancel the units and get the units that we want, especially as you get into chemistry in high school and physics in high school and beyond. You're going to be doing lots of cross-canceling of units. So literally every week this year, I'm making sure that we're doing at least a little bit of conversion factors and what they call dimensional analysis. It's a fancy way for saying cross-canceling. Okay, back to where we were today, what we started the day with, Led Zeppelin. Apart from being an awesome album, and if you're my generation, you probably know a lot more about Led Zeppelin than probably most of my students do. But they used this particular picture on one of their album covers. When you look at this picture right now, this is famously the Hindenburg going up in flames. The Hindenburg was filled with hydrogen gas. Now, when we're talking about a chemical reaction, it's a dramatic example, but I use this particular one partly because they use it in a Mythbusters I show a little bit of the clip from when they're talking about the reason that the Hindenburg went up so quickly. Also, interesting tie-in, The Boys in the Boat, that book recommendation I gave out at the very beginning of the year, they mentioned the Hindenburg in there a few times because it was floating over the 1936 Berlin Olympics there. But when you're looking at the Hindenburg, a tiny bit of a World War II story here. When you're looking at the gas that it was filled with, why in the world would they fill a blimp, a Zeppelin, with hydrogen gas? Well, it turns out some of the people back in the 1930s in the United States had kind of a clue that the United States might come into conflict with what was then Nazi Germany. And while most people were still kind of reeling from what they called the Great War, what we call World War I now, America had at least a few people who said, let's not sell Nazi Germany any more helium. We use helium, of course, in party balloons. Helium is inert. This is where we were asked to bring out our old periodic tables. We had colored in a periodic table, and we saw that as you move to the right on a periodic table, when you get all the way to the right, you have gases that you can hold flame under them all day. They're not going to explode. Hydrogen, however, was on the left side of our table. It was grouped with the very reactive metals. Hydrogen is incredibly reactive. Things on the left side of the periodic table, again, this is going back to something we saw earlier, things on the left side of the periodic table, they blow up if you just look at them funny. So why would you fill a blimp with hydrogen? Well, the engineers at the time in Germany said, fine, if we're not going to have enough helium, we'll use hydrogen instead. Now, hydrogen is less dense than helium. It does float better, if you will. It is more buoyant. However, as you can tell from obviously the picture and the little bit of the Mythbusters that we'll show tomorrow, it's much more volatile, it's much more flammable. Interestingly enough, though, in terms of the chemical reaction, I should say, not be mindful that there are real people involved in this tragedy, but in terms of the chemical reaction, this was filled with hydrogen. It reacts with the oxygen in the atmosphere. This made water. When we go over here, we look at the balanced chemical reaction and check out that this also obeys the conservation laws in chemical reactions. We start off with 4 hydrogens here, 2 oxygens on the left side. And at the end of the day, after that whole reaction, even though it releases a tremendous amount of energy, at the end of the day, you end up with water, hydrogens and oxygens combined together. Sometimes students ask, well, wait a second, if it made water, why didn't the water put out the flame? The amount of energy released is just far too great. It just vaporizes the water instantly. But when you're looking at the hydrogen and the oxygen getting together to make water, it obeys the conservation laws, the conservation of matter in a chemical reaction. Now, chemical reactions, again, at the end of the day, you end up with the same mass. You weigh it at the end of the day, the reactants and the products weigh the same. Nuclear reactions are different. In the nuclear reactions that we're going to see in this class, 1 + 1 does not equal 2. And a very, very simple way of putting it very, very quickly, let me pull up a whiteboard here and just show you just for a second. But to oversimplify the sun just a tiny, tiny bit, I asked the students to recall that you have hydrogen being forced together. And if the hydrogen is being forced together, what's the force that's pressing it together? Well, remember the 4 forces of nature. That was where we started off a few weeks ago. Gravity being one of them brings the hydrogen together after the Big Bang. Also, there is another gas law that as you compress gases, they do heat up. That's a little bit more into the high school end of things. But as we're pressing these hydrogens together under the force of gravity, they do combine to make helium. But the thing is, on the periodic table, if you weigh this hydrogen, and you weigh this hydrogen, and you weigh the helium is going to weigh just a tiny bit less than the 2 hydrogens. Again, oversimplifying just a little bit, here's the point. That's a nuclear reaction. We're going to see nuclear reactions here when we look at radioactive decay. In a nuclear reaction, E = mc² comes into play. In other words, you're taking a little bit of mass and you're converting some of it directly into energy. When I had the students outside today, feeling the wonderful sunlight here in Pacifica in the morning, enjoying a nice fall day, that's what you're feeling. You're feeling the energy of hydrogens being fused to helium and releasing a tiny bit of their mass as energy. Again, in a chemistry class, you don't do any nuclear reactions. That would be kind of on the bad side in terms of releasing far too much energy. And then finally, as I turn on the screen behind me, some of the data that we were looking at yesterday, I wanted to introduce students to data that can be predictive, but at the same time not necessarily make a straight line on a graph. So I'm just going to erase my little drawing right here. It looks something like that. You can see my glasses on the table are laying over part of the data, but we're asking the students to do this. And I chose this particular one because later on in this trimester we looked quite a bit at the planet Mars, and we talked about orbital speed and things like that. We're plotting on this side how fast planets go around the sun, their orbital velocity we call that. How fast are they moving in kilometers per second. You can find this all over the internet. You can also find it in our textbooks. And this down here, this is the distance from the sun in astronomical units. Again, this goes to the ratio thing. This is why I was having them measure, the dull in the building. We're getting really, really good, hopefully, and we will get really good over the course of the year of using ratios and using fractions. But when we put this together, we say, okay, if Earth is one astronomical unit away from the sun, and we plot the planets. We have Jupiter here, Saturn, Uranus, Neptune. I asked them to go all the way out to Pluto. And when we compare the speed of the planets against their distance from our sun, it doesn't make a straight line graph. It instead makes a curve. I didn't put in a perfect curve, but as we do our best fit line on these dots on our graph, It's not a straight line. It does make a curve, but it's still predictive. We can still use this graph to say, hey, if we were to find another planet even farther out, say 65 astronomical units away from the sun, which, by the way, there are some Kuiper Belt objects that are that far out there, we can make a pretty good prediction as to its orbital speed based on this graph. Even though it's a curve, it's not a straight line, it's not a linear graph like we've seen before, like you're seeing across the hall right now in Ms. Capello's room and Ms. Weideman's room over there in the math classes. We have seen a lot of straight line graphs. This isn't a straight line, but again, it's very, very predictive. As you notice, as you get closer and closer and closer to the sun, a planet has to go faster and faster, has to have a greater orbital velocity to maintain its orbit. Otherwise, it would plummet into the sun. So trying to get a lot of concepts across today, but really trying to bring them together this week in terms of chemical reactions versus nuclear reactions. And this right here was a little bit of practice in one, graphing data, and two, seeing data that makes a curve instead of a straight line, because as we get in a little bit more to radioactive decay, we're going to see data that makes a curve, not a straight line. And that's going to be important, especially when we get into the evolution part of this class, because when we're looking at radioactive decay, it's one of the main ways we know how old certain fossils are. Okay, that's where I'm going to leave it today. Please look for these notes online. And quick reminder, the homework tonight was simply to make sure that in addition to the notes, cut out this graph, put it into your notes, like we always do, the cut and paste thing, and I will put out the data. In other words, the actual dots of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. We're including Pluto because later on in this year, we do talk about Kuiper Belt objects, things that are out there beyond the large gas giant planets. All right, have a great day, and I'll see you online. Bye-bye.